Okay, we are officially recording, and okay, let's first, we covered several examples in last week. One thing is very important is sometimes you have information for the torque, because torque, it could be a loading, right, type of loading, and also we know the material, we know the allowable stress, allowable angle of release based on the code or the standard, something like that. And the problem is we want to design that element to the design, which means we want to pick the diameter, right? So let's just, for example, we have a shaft, just a very simple element of the shaft, right? Something like this. This could be the what chapter? It's still about torsion. We are talking about the torsion. It still is torsion. It's chapter 3. We are not going to the new chapters today. Maybe on Thursday. Right. So then his length is 2 feet. That's the length of that, right? Then instead in this problem, top allowable also given is the, let's say, 10,000 psi, and also phi allowable also is given is 0.0014 radian, and T, the torque, the torque is also given is the 48,000. This could be pound feet. It's given, and it asks us find the find the diameter of the shaft, right? Find the diameter of the shaft. So, but now let's look at these two things. Two things now is given: the allowable stress and allowable stat is the angle of twist. So for tau, we know the formula is this, right? And for the phi, formula is this, right? And G also is given. Let's see, right? G is the 12 times 10 to the 6 psi. Okay. So now let's based on each formula, find the diameter, right? So let's first focus on the shear stress, right? This formula. So tau allowable, I can write Tc over J, right? And okay, tau allowable would be 10,000. And now let's just ask some question for you. So T, what is T? T is 48,000, right? What should I write here for C? Since it asks about to find the diameter, C is the radius, right? What should I write here?
D over 2.
Right, D over 2, right? And what should I write instead of J? What is the formula for the J, if you remember?
Pi
Is
over
that
32.
Pi to the? What is the formula for J based on diameter?
pi over 32 times diameter to the fourth?
Right, thank you. Yes. So, okay, now we have this formula, right? If we solve this equation, so we can cancel out 1d here, and this would be 3, right? And then if we solve this equations, d would be 2.9 inch, right? It's diameter for the shaft, but we use only one criteria. We use we use this formula. Also, we have another formula. Let's find another. So using the formula for angle of twist, let's find another diameter, and then we adjust which diameter would be the we should pick as the diameter of the shaft, right? So let's write phi allowable would be TL over GJ. Phi would be 0.014. What is T? T would be 48,000. Okay. What is L?
2 feet.
2 feet. But since we want to get since G is based on PSI, pound per inch squared, D based on inch, let's change that feet to inch, right? 2 times 12. So this 12 means feet to inch, right? Let's write feet to inch, right? G is 12 times 10 to the 6. Question. T is given in pound, feet, and the hysteresis. Yeah, let's see. T. Yeah, I think. Sorry, you are right. You are right. Sorry, I did some mistake here. T is based on pound inch. This T. Okay. Does it make sense now? Yeah. Now I think everything is fine. Okay. Yeah. Thank you for reminding me. Okay. So J is P pi d to the 4 divided by 32. Okay. Using this equation again, if we just simplify this equation, D would be, it's very close, but the answer would be 2.89 inch. This one, okay. Okay, now I want to ask you, what do you think, guys? Which number should be picked as the answer? 2.9 or 2.89? What do you think?
The bigger one.
The bigger one. Can you explain that? What's the reason?
Just thicker and safer, in my opinion.
Okay, your answer is right, but maybe somebody said, okay, instead of 2.9, I want to pick 3 or 3.2 because that's safer. Yeah. The reason is, let me check the chat. Maybe somebody smaller one would. Okay, yeah, a smaller one. If okay, a smaller one exceeds the shear. If we pick 2.89, right? And if I, for example, if tau is TC over J, if I pick 2.89 and put the J, what's the formula for J? J is the J, the formula for the J is pi t to the 4 divided by 32, right? If I pick a smaller one and put there, and then since the denominator decrease, tau increase, and then tau would be greater than 10,000, right? And then that's bad, right? Therefore, 2.89 is not a good choice because if you put 289 in the denominator, then the tau increase, even we may reach the tau lab, we may reach the tau would be 10,000 something, 10,000, maybe 10, 10,000, 20, but it's greater than tau lab. Is not good. So because of this reason, we should pick the maximum value between these two, right? So let's just denote this one, for example, 1, this one 2. Let's write maximum of the D1 and D2 would be 2.9 inch, but it's good, it's enough. If you have a problem, if I ask you the problem is enough and you get the full credit, that's fine. But in reality, 2.9 inch maybe is not a very standard diameter, right? 2.9 inch. The standard diameter may be 3 inch, 4 inch, something. Then if the problem is a real design problem, so we should propose a 3 inch would be the good, because we should pick something in the market, right? So, but forget about that. But right now, just based on this calculation, yeah, we should pick the 2.9 as a choice, right, for this problem. Does it make sense to you?
I'm confused. So why do we pick the bigger one again?
Yeah, pick the bigger one because let's check a smaller one. Let's pick the smaller one, 2.89, right? Let me write with another color as a scratch work, right? Let's look at this formula, right? Tau is TC over J, right? T is 48,000 C D over 2, D over 2. Let's write, let's write this formula here, D over 2 over pi d to the 4 32. Let's write again 48,000. I just cancel 1d with this, would be 1 over 2 pi d to the 3 over 32, right? Now let's pick a smaller one, not the largest one. If you put a smaller one here, 48,000, right? 2.89 to the 3 divided by 32. So look at here, 2.89, the answer is 2.9 here. So we decrease 2.9 to 0.89, which means we decrease the denominator, so which means the answer for tau increase. So this answer, if you check with your calculator, for sure it's greater than 10,000, right? 10,000 is tau allowable, right? This is not good. So using this equation, we pick 2.9. But if we put 2.89, the answer would be greater than tau allowable. So because of that reason, 2.89 is not a good choice. Does it make sense? Does it make sense to you? Any Anybody? Yes.
So professor, in the real world, how it's gonna be like? What's gonna do if we pick the smallest one?
If you pick in the real world, if you pick the smallest one, then tau would be greater than tau allowable. Then
And
it's
then
not.
what's that gonna do?
So we should pick the bigger one, 2.9.
Yeah, I understand that. Like, but yeah, if it's t more than the allowable one, does that mean like what's gonna be like? What's gonna happen? It's gonna break. It's gonna.
Yeah. It makes it's risky. Then maybe it's break, it's crack, something like that, right?
Okay, thank you.
Yeah. It's risky. Yeah, it should. All the criteria should be less than allowable, right?
Professor, why do you choose 1/2 for?
Here,
Yeah.
I just cancel this D with this one,
Oh, okay. I see.
right? Does it make sense?
Yeah, that makes sense.
Okay.
Professor,
Yeah.
how is it that we have two different equations, like the shear allowable and the angle allowed, and we get the diameters differently, and then we plug it back into the shear equation?
Yeah.
Like how is it that using two different equations, we determine which one is higher and which one is lower? I mean, in diameter. I'm not sure if I'm being clear with my question.
Yeah. From the first one, we got this diameter, right?
Yeah.
And from the second one, we have this diameter. So, but if we pick the first one, if we pick the answer for the second one to this formula, then we got the answer greater than 10,000, greater than tau allowable. So which means it's not good, right?
Yeah.
But if you put the 2.9 to the second one, then that's fine. The answer would be less than 0.014 because we increased the denominator.
I guess that I understand that part, but my question is, how is the shear and the angle and the angle related?
These two related, what does that mean, you mean?
Because we use their answers in order to find what's allowed, right? In order
Yeah.
to choose the diameter. So how are they related?
So these depends of the material property.
Okay.
Or the application. For example, we have an application as said, so for example, the member is a steel, okay, or aluminum, right? Based on in the type of the steel is said in the market, it said, okay, the allowable or maximum shear stress is this value. For example, 10,000 PSI, right? And this value is different with the, for example, wood, or for example, with the other materials, some for copper. And also based on the application, it said, okay, it said we need the maximum value for the angle of twist for this application would be 0.014, something like that, right? These are the max, which means they said, okay, you as an engineer, once you wanna design this element, you should consider these two criteria. The maximum shear stress, this one, because of the material property, and because of the project or problem, we don't know about that, right? Because of the project or problem. So the maximum deformation or angle of twist is this one. So once you find the diameter, you should consider these two criteria. So these two is two actually independent things to each other. Right?
Yeah.
Does it make sense now?
Is it safe to say then that when we're looking for the diameter, can we just go straight to the shear allowable and just use that?
Yeah.
Or should we always do both equations?
It depends. If one of them is given, just go to that equation. But if both of them is given, you should check both.
Then you
equations.
have to do both. Okay.
Right. Okay. So.
Professor?
Yes.
On the exam, are you okay with us just rounding instead of like putting 2.9? We can put 3.
Say that again. 3.
On the exam, are you okay with us rounding? So instead of putting 2.3.
for this type of problem, no, because it's not a real application. Just write based on one or two digit is fine. For example, for all the problems, something, everything, just write based on one or two digit, that's fine. For example, 2.9, 2.91, 2.52, all 2.5, it is good. So don't write maybe 3, 4, 2, or also don't write maybe 2.3 to 1, 2.4, 1, 1. So these are not good. One digit and two digit is good, right? Okay.
What about for the units?
What does that mean, units?
Like if we write in like, let's say kilonewtons instead of newtons, would it matter much, or is there one specific that you prefer?
No, no worry for that. You can just write one or two digit, that's fine. If we have very, very small things, yeah, write more, maybe like that. If you have a very, very small thing, that's fine. Because then it doesn't make sense to write only 0, right? Look at this phi, 0.014 is perfect like that, right? But if you have something like 5.876.523, yeah, yes, you can ignore this one. That's fine, right? Does it make sense?
Yeah, thank you.
Mm-hmm. Let me just erase this scratch. Okay. Let me, I shared, I put something in the black, but for the next example, let me share my, I also put this example in the blackboard. It's very difficult to show with, yeah, here in the blackboard I put there. But let me share my screen. Here, yeah, drawing this one, it looks like 3D is something is difficult. Let me just upload this example. We can talk about this example with this file. So we have something like this. Say we have these two shafts are connected by the gears, right? This is one type of I think we have one homework problem, something like this, right? And then when apply the torque here, only fixed point would be this point. I think that's point F. This is the point F. The only fixed point here, right? So yeah, this is point F here. Here is not fixed, it could be rotate, right? So in this problem, we want to find the angle of the twist. Angle of twist at this point A, right? The angle of twist when they apply the torque, we want to find the angle here. So in this type of problem, always once we have the gear, something like that, you should draw the free body diagram with the separate. So we have two shafts. So first, draw the free body diagram in the separate figures, right? So, which means this is a free body diagram for the first shaft, and this is the second shaft. And now I need to explain about these details. How can we model these details, right? So if we have this shaft, right? So we apply the torque here, and then this one is rotating, this gear, and also this one is rotating. So if we show in the two separate shafts, right, something like that, right? So that's a torque, that's good. This is the shaft, and then this is the gear here, right? So this is a free body diagram, right? What's the definition of the free body diagram? Free body diagram is a diagram to show all the forces and the moments, right? In the statics, you learn about that. So here we have this gear, but actually once we apply the torque here, also is rotating. So now to show that it's rotating, we should show this force, right? What is this force? This force could be the reaction force between these two gears. And now look at this force, P. P times this arm, it makes the rotating, right? P times this arm. Okay, P times this one. Now this free body diagram is complete, right? So, you know, for example, in the statics, something like this. Once we have something like that, right? Maybe something like this, right? Once we remove the supports and instead we put the force of the supports, right? Or if you remember in the statics, sometimes we have the beam something like that, right? Maybe two beams together. So then once we show each beam separately, then we put the reaction for that, and for the lower beam reaction like that. So the same as here. Here we have two beams, but here we have two gears, right? And we know it rotates. So once we separate these two shapes, we should show a force. That force makes the rotation, right? So which means this force play the role of this gear, and this force to play the role of this gear. And so because of the equilibrium, these two should be the same, right? Look like this. If we have two beams, if this is, for example, this R, because of the equilibrium, we have this R also here for this, right? So now is the free body diagram for the first shaft from point A to point C, right? And then, okay, for each free body diagram, let's just write the, okay, let me say something. Let me say something. So once we want to find the angle of twist. So if you remember, for example, we have before we have something like this, right? For previously, we have, for example, this shaft, right? And this shaft, for example, and maybe we have forced rotation here, and then here, and then here, right? This is a fixed point. And then we make a section for each one, and then find, for example, if A, this is B, this is C, this is C, this is D, and then we said, okay, angle of twist is angle of twist phi AB plus phi BC plus phi CD, right? That's a procedure we did before, right? So the reason, find the angle of twist AB. What does AB means? A respect to B, and B is rotating, right? B respect to C. C is rotating. C respect to D, and D is fixed points, right? So which means then we reach the fixed point, and then we add these three together. But the problem here, A, okay, is rotating, this one is rotating, and also C could be rotated. C is not a fixed point, right? The only fixed point in this mechanism, in this structure, is F, right? So which means we should also employ the second shaft to find the angle of twist. And now I wanna show you how can we solve this problem. Because if you look at the first shaft, just look at the first one from A to C. All the points could be rotating. There is no fixed points, right? So which means here we fix C to the D. D is a fixed point. So we find the phi, and then find B to the C, then find A to the B. But here we are not, we can find A to B, B to C, but C is also rotating. At point C, we have a rotation, but we are not able to find the angle of twist at point C, right? So we need to employ this case. And now let me explain how can we solve this problem. It's slightly different with the previous problem. But so what does that mean? Let's look at the second one, right? Before solving the problem, let's look at the second one. Second one, okay, in the second one, it's fixed points, right? F is the fixed point. So if in the EF, we can find angle of twist at point E, right? In these sections, right? Because F is a fixed point. So which means this one the second shaft could be modeled as all the problems already we learned, right? Because for all the problems, always we have a one fixed point, right? So you find the B, C respect to D, B respect to C, A respect to D, and fine. But here, that's okay. So the purpose of this problem, we want to find the angle of twist for at point E, and then based on the angle of twist here, we find the angle of twist for the first shaft, and then based on that, find the angle of twist at point A. That's it. We are asked about that, right? So the procedure is slightly different, but another problem is we have some additional unknowns, because okay, this torque is given, but now since we draw the free body diagram, we have additional unknown P, right? This force, because this force makes the torques here, right? And if we want to find the angle of twist for the second one, so we need a torque, right? This torque, and the torque is unknown because the P is unknown. So the purpose, so now the purpose to draw the free body diagrams for these two shafts is to find this P, and once we find this P, then we can, okay, refer to this chapter, the torsion chapter, and find the angle of twist. And then I need to explain to how to find the angle of the twist for the first shaft, right? So it's slightly different with all the problem we already solved by now. So now in the first step, now back to statics, right? Just only to statics. So free body diagram. So look at the first shaft. Look at the first shaft. So we have one unknown P, right? Summation of the torque is, and instead of mx, I do like to write summation of torque equals 0, but that's okay. You can write summation of the moment in x direction. But I usually like to write the summation of the torque, right? So this torque, 1.2, and this torque, P times the R, would be in opposite directions, right? If this one, the direction of this one is in that direction, like the direction of this torque would be in that direction, right? This one, look at this P times this R in the opposite direction of this. So I put the negative. So the question is, what is this? The arm is, we should measure the arm to the center of the shaft. 4.5, so the shaft is look like this. Look at the section. This is a gear, this is a shaft, right? This is 4.5 inch. This diameter of the shaft is 7/8 inch, right? Therefore, the center, so the arm to the center would be 4.5 inch plus this radius. This radius is 7/8 divided by 2. So because of that reason, is right 7/16, right? So that's arm from this point to the center of the gear, right? So using that equation, then using this equation, we can find this P. Okay, we write the equation, the equilibrium equation for this free body diagram to find P, and since this P is equal with this is the same reaction. And now using this P, we can find this torque, right? So look at here, we have the fixed point, we have it, which means we have a support here, we have this torque, and the index would be F because this point is F, set at TF, right? So P is from the previous one. So then using this calculation, we can find this torque, right? So or yeah, we can find this one. And so that's the purpose of the free body diagram. So that's from just the free body diagram. It's not a material, it's just it could be something like statics, right? And now, okay, we have the torque P times this one is 1.56. So we are able now find the angle of this twist at point E, right? Phi E would be TL GJ, right? We have T is fine. We find T is 1.56 and L is given G and J, right? So let's find the angle of twist. This is torque L. Look at L. L is 12 inch. Let's say. Yes, yeah. The torque would be the same. Here would be the torque here in this shaft. Here, this torque would be exactly the same torque. This torque exactly would be the same. This torque TF, we can just write this. This would be the same, right? Because we have P times this. Right? Does it make sense? So the torque here at point E would be the same at torque F, right? Because there is no other torque between E and F, right? Look at here, there is no other torque. So then phi E, yeah, phi E would be TLGJ. TLGJ. And now we want to find phi E, the angle of twist at point E, right? So this is T, we find here. L is 12 inch, G is given, and J also I think it calculated at the beginning here. Just pi d to the 4 divided by 32. That's a J, right? This value. So then angle of twist would be 0.029 radians. Okay, now maybe after this step, everything would be new, something would be new for you. Phi E equal phi E F. The reason because phi E equal, there is no other torque here. There is no any new section. There is, the material doesn't change, nothing. So we can make one sections, right? If we find the one sections of phi E F equal phi E, right? If you have additional force here, some other, yeah, thank you. It means if you have additional torque, you should make another section, then phi E would be phi E, for example, to K and plus phi EK and phi KF, something like that. But since between E to F, there is nothing, just would be the same. Right? So now phi E is the 0.029 radian. And now, okay, back to the, okay, we find the angle of twist in this gear, right? In this shaft and this gear. And now let's, okay, since we have angle of twist here, using just the geometry, just calculus, using geometry, we can find the angle of twist on this part, right? And now, because we need the angle of twist here, because we want to find the angle of twist at point A, right? So now, again, forget everything about material, and now just back to calculus, to the geometry. So this is the big gear, this is a small gear, these two. This is a big gear, this is a small gear, right? So angle of twist for the big one, we find it 0.029, right? This one, right? And the purpose is to find the angle of twist for the smaller one, for the first shaft. So we can use the triangle, right? So we have this angle, right? We have this distance, right? So we can, so let me write in the larger scale, maybe it would be better. Scale, let's see. scale. Okay. So this is phi E. This is phi B. The purpose is to find phi B for the first shaft. Phi E is given, right? Phi E is 0.029, right? And also this length is given, right? Because we have this diameter, the radius of this. So this one is 6.4375, right? Therefore, we can find this length h, right, as this calculation, right? H divided by this would be phi E, or tangent. Tangent phi E equal phi E because, you know, at the beginning of the semester, we said, as shown, we are in the elastic range, which means all the rotation, all the deformation would be very, very small, less than 6 degrees, right? So therefore, tangent of the angle could be equal to angle. Tangent angle, angle, sine angle would be all the same, right? So we can find the h for this. So h would be phi E times this length, right? This length would be 6. I don't need to write here. 6.4375. And since we have h, and also we have this length is 4.9375, then we can find the angle of twist for this. So that's the things we are looking for, the angle of twist for the first shaft. So using this equation, right? So these two numbers, we can find this. These two numbers are given because we have, this is the 4.5 inch, this is a 6 inch, and half of the 6 inch plus half of the diameter of the shaft, then would be this number 6.4375, and 4.5 plus the half of the diameter of this shaft also would be this number. So then, okay, using this two triangle and this h between, so then we can find phi B, right? We can find this one, right? So, and now after this step, again, we want to back to our chapter 3 to find the formula. So now let's back to the first shaft. So for the first shaft, we have angle of twist here, right? So then what is phi A now here? Let's write with the other color. Phi A would be phi AB plus the angle of twist here, right? Angle of twist here is fine, right? So, and we find the phi B right now. And now one more step is to find phi AB, right? So that's the reason I use a second shaft, because if I want to write phi A equal phi AB plus BC, but the problem here is not a fixed point. C, we cannot find angle of twist as C because it's rotating. But now we use this one, we find phi E, and now we find phi B. So phi B is given. So phi B plus phi AB would be phi A, right? And phi AB between these two, make a section between A and B. So everything is the same. So phi AB would be just TL over GJ, right? So between A to B, just TL over GJ, T is given. L is 14 inch, right? Let's check. Here, between A to B, this 6 and 8 is 14 inch, right? A to B, 14 inch. It would be 14 inch. This is G, and this is J. So then if you solve this one plus this, that would be 0.0639. Is enough for answer. You don't need to change to the degree. That's fine. But if you're asked, you can just multiply 180 divided by pi, right? So this problem is different. So for some steps, we need to use a geometry formula, not material formula, something like, yeah, this for this part especially, right? And at the beginning also, we need to draw the free body diagram to find the torque. The reason is to find the torque for this shaft, right? So question, guys? For this problem? Any question? So, okay, let's go to the, can you see the whiteboard now?
Yep.
Okay, thank you. So, okay. Yeah, just ask me if you have a question. Maybe you can ask me also later if you have the question. So one thing left for this chapter is, if you remember from chapter 2, one important application that was the indeterminate bar, right? Or indeterminate rod. In this chapter also, one important thing is what happened if you want to find reactions for indeterminate torque, indeterminate shaft, right? So the procedure, it would be exactly the same as the previous chapters, but with the equation for the torque, right? So which means we want to use the principle of the superpositions, right? So let's just draw a problem. Let me just draw a problem and then discuss about how can we solve the problem, right? So let's, for example, we have maybe one support here. Then we have a shaft here. And this shaft, okay. Let me draw nicely. Okay, maybe it would be better. And then we have another support here. You know, for all the problems we already solved, we have one fix, and the other part would be free end, right? But here we have two fixed, right? Let's see. Also in this shaft, from this support to there, we have just a hollow section also. The sections would be hollow. So it would be something maybe like that, right? And the rest of the solid sections, this would be A, this would be B, and this point C, right? So let's write there. Let's put this is 2 meter, and this is 3 meter. And this would be the 50 millimeter is the diameter of the shaft, and sorry, it's 100 millimeter. 100 millimeter. And the inner diameter for this hollow sections would be 50 millimeter, right? So, okay, this problem, so that's the application. So in this problem, we ask find find the reactions. Let me check. Okay. Find just the reactions, right? Only. Right, so let's just denote the reaction. For example, we have one torque here is at TA. At A would be TA. Let's hit that direction, TA. Also, I forgot to draw the loading. So loading would be the torque. Let me draw the torque with the other color to make. So we have a loading, this torque here. And the torque in this problem is given based on 30 pi. That's the answer. That's a given number. No, 30 pi. The unit is kilonewton meter. The pi is 3.14, right? You can multiply 13 times 3.14, right? It's not a big deal. So, okay. Let's see. So if you look at this problem, statically, if you want to write the summation of the torque equals 0, so we can say, okay, TA plus TC equal 13 pi, right? It would be it would be the 13 pi, right? So let me just guys, I just sign out my chat numbers. Sorry, guys. So, sorry. I think there is something wrong here. So, okay, but the problem is how can we find the TA and TC, right? Because two problems, two unknowns, right? Just the two unknowns, TA and TC, with the one problem. So again, we should use the superposition. What does that mean? Which means just release one reaction, remove one support, and then shows based on the reaction, and then solve that problem, and the other structures just based on all other external forces, right? So we can solve something like this. So by superposition, let's just write like this. By superposition, we can just okay, and instead of this figure, we can write maybe like this. Yeah, just draw this one first, right, like that. Right. And the torque is here is 13 pi. So by superposition, it's plus, all right, like this. And then now just write just this load, TC, right? So now, okay, these two, look at these two figure. This two figure is equivalent this one, right? Just for this one, we write this one based on external forces, external torque is 13 pi. And this one based on this force, TC, and TC is the reaction, right? This TC equivalent, this supports, right? And now for each one, we can find the angle of twist. So this point C, right? For this one, we can find angle, we can find phi C for this one. And for this one also, we can find the angle of twist at point C, find another phi C, right? Let's index phi C1, phi C2, right? But here we have support, right? Which means the angle of twist is a deformation, right? There is no deformation because it's a fixed support. The angle of twist is 0, right? Which means phi C1 plus phi C2 would be the 0, right? So phi C1 plus phi C2 equals 0 because here is a fixed support. There is no deformation. Angle of twist is a rotation, right? There is no rotation, nothing at point A and C. So first solve this problem, find phi C1 first, then solve this one, phi C2, and then add together equals to, and the phi C2 would be some parameters based on this, right? It's exactly the same as the chapter 2. In chapter 2, we solved this problem, if you remember, based on the delta, right? Delta 1 plus delta 2, and delta 2 would be the function of P force. And here, but the rotation for this structure would be based on function of this, right? So now let's just first focus here. First focus on this structure. Let's write this one, structure 1, structure 2, right? So so first structure 1, let's see, we have this one. We have let's see here. Okay, 13 pi. Okay, this is a C, and this is B, and this is, and now let me ask a question, guys. How can I find, what's the procedure to find the phi C? Does anybody know? So look at this as a separate problem, maybe from something like last week, something.
Using the shear stress?
No shear stress. We want to find phi C. We want to find, the purpose is find the phi C here. Phi is TL over GJ, right?
Yeah.
So from point C to point A, just make a sections, right? Yeah, sum the sections, right? So from point C to B, we can make a sections to find phi CB and find phi BA, right? So phi C would be phi CB plus phi BA, right? Plus phi BA. So guys, if I make a section on CB, there is no force, right? In the section CB, if I make a section, there is no torque here, right? So TCB is 0, which means phi CB also is 0, right? Nothing here. Let's write.
Can you explain that one more time, the CB part?
CB, at CB, if I make a section here, right? If it's this is C, there is no torque here, right? Between C to B, right? So summation of the torque, if summation of the torque equals 0, right? If the summation of the torque equals 0, if you have, for example, TCB here, right? So TCB is 0 because there is no torque between C to B, right? Right?
Mm-hmm.
So then TCB is 0, so phi CB would be TL over GJ. CB, since TCB is 0, this phi CB also 0, right?
Okay, it makes sense now. Thank you.
Okay. Now for phi BA. For BA, okay. For phi BA, if you make a section, yeah, we have this torque, right? The torque is 13 pi. So phi BA would be TL GJ and AB, right? What is T? T is 13 pi. What is L? Does anybody know L? The value of L?
2 meters.
2 meter, right? It's 2. Okay. 13, let me say something else. 13 pi is based on kilonewton, right? I give you the values. Let's multiply to 1000 also based on Newton. And L is 2 meter, right? Also in this problem, G also is given. G is given is 80 gigapascal. 80 gigapascal, right? Just add G is 80 gigapascal. Okay. So let's write the G is 80 gigapascal. And 80 gigapascal means 80 times 10 to the 9 to show based on Pascal, right? What is the J? JAB would be pi times 100 millimeter means 0.1 meter, right? To the 4 divided by 32, right? That's that number would be 0.10 radian, right? That's phi B. So phi B, phi C, phi BA, phi CB plus phi BA. Therefore, phi C would be 1.4 radian, right? What does the numerator say? 13 pi is given. 13 pi is the torque. The torque is given based on pi. I think this problem is given based on pi because it's easy to cancel, right? This pi could be canceled with this. This 13 pi is given, is a given value. I already wrote here, 13 pi. Does it make sense?
Professor, convert the millimeters to meters down
What?
there.
Say that again.
Isn't the diameter given as 100 millimeters?
Yes. I change it to meter.
Oh, okay, I see.
Okay, right? So this is for a structure 1. For a structure 2, it's just Right, let me draw the structure too. Again, for the superposition. So here we have, let's see, TC. I said TC here, but okay, now we have a hollow section here. So what do you, okay, TC, let's see, BA. Okay, here again, phi C would be phi CB plus phi BA, right? Because we have two sections. In this section, we have a hollow section. Here we have a solid sections, right? So for phi CB, so for each section, if you make a sections, right? For each sections, if you have TC here, then if this one, for example, TCB, right? And summation of the torque equals 0, TCB equal negative TC. This is for section CB, right? For section BA, let's see, we have a hollow section here. For section, so we have one section here, one section here. For this section, again, if this is TBA, and this is TC, summation of the torque 0, summation of the torque would be the 0, TBA would be negative TC, right? So phi C, now let's find phi C, phi CB plus phi BA, right? So phi C. What is phi CB? Phi CB would be, TCB is negative TC. What is LCB?
3 meters.
3 meter, exactly. G would be 80 times 10 to the 9 times. Okay, for CB, we have the J for the hollow sections, right? If you remember from the last lecture, we have something like that, right? Sorry, it's 4, right? That's for hollow section, it would be 4. This is for this one. And for BA, again, negative TC. What is L of BA? It's 2 meter, right? This is 2 meter, this is 3 meter. 80 times 10 to the 9. But J, here we have a solid sections. Just pi divided by 32 times 1.4 to the 4, right? So again, here we have a, let me write with the mention with the other color. Here we have a hollow section in the BC. Just I wrote like that, minus the inner diameter, right? That's a formula. And this one, just we have a solid section. So just BA, I'm like that, all right? So if you find the phi C in this case, would be the The answer would be negative 6.62 times 10 to the negative 6 TC, right? So based on TC. So in previous page, we said, okay, we can index this one VC1, index this one, for example, VC2. So now we are almost done, right? Because VC1 plus VC2, because of the superposition, right? In this page, we said it would be 0 because in reality we have fixed support here, right? VC1 plus VC2 is 0. So let's write here VC1 plus VC2 equal 0. What is VC1? VC1 is 0. Plus VC2 negative 6.62 would be negative 6.62 times 10 to the negative 6 TC. And now is interesting. Using this equation, we can find TC, right? What is TC? The answer for TC I have is 15,707.6 Newton meter. Okay, and now let me ask a question, guys. Okay, we have this shaft, right? We find TC, and how can we find TA? This is TA, this is TC. How can we find TA?
What's our first equation?
First equation, again, let's back to the first equation here. Because of the equilibrium, TA plus TC is 13 pi, right? It's a static. So using this equation, let's denote this as a star. So let's using the start of that equation. We know the TA plus okay, 15,707.6, 13 pi, that equation, but 13 pi, that was kilonewton, right? 13 pi, let's just multiply to 1,000. This 1,000 means kilonewton to Newton, because TC is based on Newton meter, right? If we solve this equation, TA would be 25 Newton meter. So that's the purpose of this problem, right? Find that's application, indeterminate shaft using the equation for angle of twist. So then find the both reactions, right? The purpose was this one, right? TATC, use a superposition, exactly the same as the chapter 2, but instead of equation for deflection, we use equation for rotation, for angle of twist. Superposition, structure 1, structure 2. This is a structure 2, right? This is a structure 1. So we find this one, this is VC1, VC2, and then equals 0 because at point C, actually we have support, right? Does it make sense to you guys? Question if you have. Let me stop recording, then if you have a question.